Have you ever wondered how a doctor determines the likelihood of a disease based on a test result? Or how artificial intelligence systems like spam filters classic emails as spam or not? The answer lies in Bayes' theorem, a cornerstone of probability theory and decision making under uncertainty. Bayes' theorem was introduced by Reverend Thomas Bayes, an 18th century statistician and theologian. Although his work wasn't published during his lifetime, it gained significance after being formalized in 1763 by Richard Price. Today, Bayes' theorem is a fundamental tool in fields like statistics, machine learning, and data science. It provides a way to combine prior knowledge with new evidence to update probabilities, making it invaluable in a world filled with uncertainty. Before Bayes, probability was largely focused on games of chance, rolling dice, flipping coins, and drawing cards. Bayes' innovation was extend to probability to real world problems where new information updates our beliefs. For example, in the 19th century, Pierre Simon expanded Bayes' work using it to predict celestial movements and estimate the masses of planets. Today, Bayes' theorem is the backbone of decision-making process in fields like medicine, where it helps doctors access diagnosis, and AI, where it powers recommendation systems, spam filters, and even self-driving cars. Let's break down Bayes' theorem step by step. At its core, Bayes' theorem allows us to calculate probability of an event given some evidence. Here is the formula for this theorem. Probability of A given B, the posterior probability of an event A after observing evidence B. The next is PA, which means the prior probability of event A, representing what we initially believe about A before seeing the evidence. Vice versa, the probability of seeing the evidence B if A is true, and then P probability B. In simple terms, Bayes' theorem updates our initial beliefs prior probability based on new information to produce a revised belief posterior probability. Imagine a situation for an practical example. Imagine there is a rare disease that affects only 1 in 1000 people, that is 0.01% of the population. A diagnostic test is available which correctly identifies the disease 99% of the time, true positive rate. However, it also has a 5% false positive rate, meaning 5% of healthy individuals test positive. If a person tests positive, what is the probability they actually have the disease? Here's how we solve this using Bayes' theorem. First, prior probability P disease, which is 0.001, which means 1 in 1000. Likelihood P positive disease, which is 0.99, true positive rate. Third, P no disease, 0.999, since 99.9% of people don't have the disease. P positive no disease, which means 0.05 false positive rate. Now after this, calculate the total probability of test positive, and finally use the Bayes theorem to find the posterior probability. So it can say that so we can say that even with the positive test result, there is only a 1.94 chance chance the person actually has the disease. The highlights how critical it is to consider prior probabilities when interpreting diagnostic tests. Bayes' theorem has far-reaching applications across various domains like medical diagnosis, machine learning and AI, finance, law, and in everyday decisions. But there are some strengths and limitations for this theorem. The strength is it is grounded in a solid mathematical framework and works well with limited data, especially in iterative processes like machine learning. But there is a limitation. It which is its effectiveness depends on accurate prior and reliable data, Misjudging this can lead to misleading results. For instance, in our disease example, if the prior probability was overestimated, the posterior probability would be inflated. In summary, we can say that Bayes' theorem is versatile and elegant tool for decision making under uncertainty. It updates our beliefs in light of new evidence, making it indispensable in fields like medicine, AI, and finance. Whether you are a data scientist designing algorithm or simply deciding whether to carry an umbrella based on weather prediction, Bayes' theorem helps make sense of probabilities in a complex world. Thank you for watching.